This is a lesson on rotational kinetic energy in the work and energy unit and in the rotational dynamics unit. We're bringing together a lot of concepts when we think of the idea of rotational kinetic energy. The first of which I wanted to remind us of the conservation of energy, which I motivated from the work kinetic energy theorem. And you are likely not to see this equation very frequently, but for me it arranges the idea of what conservation of energy is, using the idea of energy states, an initial state and a final state in terms of state functions. And this is pretty much just accounting for energy. We have some sort of initial energy state, which we can quantify in terms of kinetic energy and potential energy. We take into account any energy in or out of a system, and that will equal the final energy state accounted for in kinetic energy and potential energy. And we've seen already that there are several forms of potential energy. There's gravitational potential energy we can do near an Earth's surface as opposed to in outer space. We can do spring potential energy. There are many types of potential energies. With rotational kinetic energy, we're going to add in another type of kinetic energy. Just like translating objects have translational kinetic energy, and we looked at this in the work energy theorem lesson, 1/2 mv squared. We have an inertia term, and then we have a speed term. Rotating objects can have a rotational kinetic energy. And notice that there's also an inertial term, the moment of inertia I, that's what that is, a moment of inertia. And then omega is the angular velocity. Again, very analogous to the translational. And so at this point, I start denoting the difference between the translational versus the rotational kinetic energy. We may need to take into account different moments of inertia depending on different systems that we take into account the kinetic energy of. We could have multiple objects, or we can have an object that's not rotating about its center of mass but at some other point. The benefit of rotational kinetic energy is that it can be used in the equation that I already derived for conservation of energy. It's just another kinetic energy term. The example I've chosen for us, Grindstone, exemplifies how to take into account kinetic energy when there's work involved. A grindstone with given mass and radius is spinning at 3,600 RPM when the motor adds an additional 82 joules to increase the speed. Okay, so we have an initial energy state, we have some sort of initial motion. There's some work added to the system, and we will have some sort of final energy state where they want us to find what is the final angular speed of the grindstone in RPMs. I see that they gave me an initial RPM, an initial angular speed, omega initial, equals 3,600. I'm going to write revolutions per minute. If we're dealing with joules, I want to get this quantity to SI, so I'm going to change this to radians per second. 1 revolution is 2 pi radians, and 1 minute is 60 seconds. And when you multiply that out, this becomes a 60. It cancels with this 60, and I'm just going to leave it as 120 pi radians per second. I'm just going to leave it like that and plug that into my calculator. I don't have to make any decisions about rounding right now. That's the benefit of doing it that way. I'm going to notice other information they give me in the problem. The energy in the work by the motor is 82 joules. That's just a number that I could plug into an energy equation. The other thing I see going on is dimensions of my wheel here, the grindstone. It's spinning at some omega. And if I wanted to consider rotational kinetic energy, I have to think about the moment of inertia. So I'm going to assume the grindstone is a disk, and the moment of inertia for a disk is 1/2 mr squared. So I'm just going to write that down and plug in numbers later. The R value is given in centimeters, so I will convert that to meters. And the mass is fine. So when I think about writing what I know into this equation, right? The initial energy state, the final energy state, and energy added. I don't have to consider potential energy. It's just a grindstone turning. The center of mass is not moving anywhere. So my potential energy terms will be 0. And so I will have an initial kinetic energy term, some work added by the motor, and a final speed associated with having sped up. So let's write those terms in. 1/2 I omega initial squared plus this work done by the motor will equal 1/2 I omega final squared. They're asking me to solve for omega final. I'm going to move things around and plug in what I know. I can write out omega final squared equal 1/2 I omega initial squared plus this work done by the motor divided by 1/2 I. If I distribute this into these two terms, this will simplify to omega initial squared plus work of the motor over I, which is 1/2 mr squared. So I can write this equation down and plug in numbers. So let's see, omega initial squared is, remember that's that 120 pi. I'm going to square that whole quantity. Plus 2 times 82 is the work of the motor, divided by 1/2 times the mass of the disk, which is 1.1, times the radius of the disk squared, which is 7 centimeters. Take a square root of all of that, and when I solve, I get omega final equals 440.1663 radians per second. But I want to do the conversion back to RPMs. They asked for the final answer in RPMs, so I can reverse my unit conversion, and I get 4,203 RPM, which is about 4,200 RPM. So you can see that instead of translational kinetic energy, we can put rotational kinetic energy into that term in conservation of energy. One caveat that I need to introduce to you is the idea of rolling without slipping. With the grindstone example, we didn't have to think about the center of mass moving anywhere. It was just spinning in one spot. But oftentimes objects are spinning and moving at the same time. So you would have a kinetic energy term that would be a linear or translational contribution, and a kinetic energy term that would be a rotational contribution. It has both types of kinetic energy as it's moving along. So there's the velocity of the center of mass, and there's an omega. And often these two terms are not related to one another. An example would be a bowling ball, where it would be spinning on its axis as it moves in a direction, and those two motions are not related to one another. Spinning this way and moving that way, it could spin in one spot, or it could roll in a direction, and those two things are not related to one another. In the special case of rolling without slipping, they are related to one another. Through the good old equations we know for relating linear motion or translational motion to angular motion. The displacement is related to the angular displacement, the velocity is related to the angular velocity, and the acceleration is related to the angular acceleration. In the case of rolling without slipping, you will need to look for those words in the problem. If they are not there, you cannot assume that it's rolling without slipping. A condition needed for rolling without slipping is adequate torque. If you're on a frictionless surface, you will not be able to have adequate torque in order to cause the center of mass motion for it to roll without slipping. The problem I've chosen to exemplify this concept is two wheels. Two identical wheels are moving on horizontal surfaces. The center of mass of each has the same linear speed. So I can label this vector forward from the center of mass V. However, one wheel is rolling while the other is sliding without rolling on a frictionless surface. Okay, so let's let this one have some sort of rolling as well. And I know that this is going to have friction with the surface. Where over here, this is a frictionless surface, I'll put mu equals 0, and this one's just sliding along. Like the same point is in contact with the floor and it just slides along like a box would. Each wheel then encounters an inclined plane, so I put that in the diagram. One continues to roll up the incline while the other continues to slide up. So this one's still just sliding up. This one's rolling while moving forward. Eventually, they come to a momentary halt because of the gravitational force that slows them down. Okay, so they each go up some height, and I'm thinking about energy, and I'm thinking about, okay, how high will they end up going because of gravitational energy? And I'll call this H1, and I will call this H2 for the first and the second. As the wheels move on the horizontal surfaces, which, if either, has the greatest total kinetic energy and why? Okay, so let's think about what's going on in the initial energy state. In the initial energy state, we're going to have two types of kinetic energy. Kinetic energy initial is going to be the kinetic energy translational plus the kinetic energy rotational. And I can write values in for here. I'm going to write in the symbols 1/2 I omega squared plus 1/2 mv squared. So that's for the first situation. In the second situation, when I look at the kinetic energy initial, all I have is translational kinetic energy, which is just 1/2 mv squared. M and V are the same, so I can see that because this wheel is rotating, it has this rotational energy. I can say for A, the kinetic energy for the first situation is going to be greater than the kinetic energy for the second situation. When they come to a momentary halt on the incline, which, if either, has the greatest potential energy? Justify your answer. Let's write down the conservation of energy equation for each of them. Initially, they both have 0 potential energy, and I know that there is no non-conservative forces acting on the incline to take energy away from the system. The final kinetic energy, it says both of them comes to a halt, so the final kinetic energy for both of them is going to be 0 as well. So I get this equation, kinetic energy initial equals potential energy final, which tells me whichever one has the higher kinetic energy has the higher potential energy. So I can write that down. Potential energy 1 is going to be greater than the potential energy 2 because there's more energy to begin with this additional rotation. Which wheel, if either, rises to the greater height? Explain. Okay, well, I'm going to keep working with this equation here, and I'm going to have two versions of it. The first case is the case where we have both rotation and translation. So I can write down those terms, 1/2 I omega squared plus 1/2 mv squared equals mgh1. In the second case, I get 1/2 mv squared equals mgh2. Okay, so when I look at this, and you may not even feel like you need to justify any further because it's evident in the equation, there's more terms on this side for calculating H1 than there are here. This same term is this one, and then this height has an additional rotation term. So I can say H1 will be greater than H2 due to the additional rotational energy.